Hello and welcome back. Today we are going to discuss the first practice problem on DP. In this video and the upcoming videos, we will try to follow a set pattern. We'll first try to understand the problem statement, then come up with a recursive solution, analyze that solution, optimize it using memoization. Then we'll try to write the recurrence relation and finally write the tabulation solution using that recurrence relation. So let's quickly go through the problem statement. It states that you are climbing a staircase and it takes n steps to reach the top. Each time you can either climb one or two steps. In how many distinct ways can you climb to the top? So now we have distinct ways of climbing to the top because at each step we have two options. Either we can take one step from there or two steps from there. So let's say, for instance, we have two steps total, one and two, and we start from zero. So there are two ways of reaching the top, which is two. One is that we move to step one and then we take another step to step two, or we directly jump to step two by taking two steps. So there are two ways in total of reaching to the top. Now, how to solve it recursively? We can very simply apply the universal intuition that we have learnt in the recursion series. We can assume that a recursive method works for the remaining problems and it will return the correct answer for the remaining subproblems. We just need to take care of the current step. Using the answers returned by the recursive method, which we assume are correct, we have to generate the current answer. Apart from this, we just need to take care of the base case. So let's say that we are at step x. The next step is x plus 1, and then we have x plus 2, and then we have the top. So let's say that we can reach to the top from x plus 2 in total y ways. So there are y different ways. And from x1 to top, there are z different ways. And we know that our recursive method is going to return us the correct answer for these subproblems. So x, z, and y is going to be returned by the recursive method. We just need to calculate the total ways of reaching the top from x using these z and y which have been returned by the recursive method. So from x, we can either jump to x plus 1 or we can jump to x plus 2. So the total number of different ways x to the top are actually going to be z plus y. So using the solutions returned by the recursive method for the subproblems, we have calculated the answer for the current state. Also, the base case is when I have reached the top or I have reached a cell before the top. So when I have reached the top, it implies I have found one way. So return one from there. And when I have reached the step before the top, I can only take one step. There's only one possibility that I take one step and reach the top. So which again gives one more way. So whenever we reach the top or the second last step, we just return one from there as these are the base cases. Now the code here is implementing the exact same logic, just it is viewing the problem as going from n to 0, which is exactly the same, just the staircase is reversed. Reason for doing this is that we can use the same method as the recursive method instead of making a helper function, because if we want to start from 0, then we would need a helper function receiving the input parameter as 0. So we could have also solved from 0 to n in this method only by taking complementary with n at every step, but that would have been just too confusing while explaining. So that's why I have just reversed the question. So now it is reaching the bottommost stair from n to 0. So we have to find the different ways. Now, as we discussed, the code is pretty simple. So we assume that a recursive method works for the subproblems. So the two subproblems are total number of ways of reaching from n minus 1 to bottom and from n minus 2 to bottom. And once our recursive method returns answer for these two subproblems, we assume that the answer returned by recursive method is correct. We just add these two answers to get the answer for the current step and return that answer. And as we discussed, the base case is going to be when we have reached the bottommost step or the step just above that bottommost step, because in both the cases we have found one way of reaching to the bottom, so we simply return one from here. So when we submit the code, it gives time limit exceeded for input 44. So let's try to make a recursion tree and analyze the solution. Let's try to make a tree for n equal to 5. So let's say that n is equal to 5. Now n equal to 5 will depend on two subproblems, which are going to be n minus 1, that is 4, and n minus 2, 3. 4 is again going to depend on 3 and 2, and 3 is going to depend on 2 and 1. Now 3 again depends on 2 and 1, and 2 depends on 1 and 0. Again 1 is the base case, so we'll return from here directly. 2 depends on 1 and 0 again, and 2 again depends on 1 and 0. We can clearly see that we are calculating certain subproblems again and again. So as you can see that n is equal to 3 is calculated more than once, n is equal to 2 is calculated so many times. So this is the problem of overlapping subproblem. And also clearly this tree is a directed acyclic graph. So we can very well apply DP for the solution. Now let's start with memoization. We can easily use a map to store the answer for a subproblem so that we don't have to solve it again and again. So let's go through the minor code changes we need to make to apply memoization. So as we discussed that we'll add a map to apply memoization. For add, we have declared a map, and then we are simply again using the same recursive logic that the recursion method will give the correct answer for the subproblems, and using that we make the answer for our current step. Now, one additional thing that we are doing here is that once we have calculated an answer for a subproblem n, we are storing the answer in a map so that we don't have to calculate the answer for this subproblem n again and again, and the answer will be there in the map. So once we have calculated the answer, we have stored it in the map and we return the answer for the current step. Now our base case is exactly the same when n is equal to 0 or n is equal to 1. One additional step that we have added is there we check if we have already solved this subproblem or not. If we have already solved this subproblem, then the answer for this subproblem will be already there in the map, and we do not need to move to our recursive logic to calculate the answer again. We can simply return the answer stored in the map and return from here. So that is how we apply memoization in our solution. Now let's write the recurrence relation for our solution. So let's say that the function f returns the number of ways to reach the bottom. Then f of n is going to be equal to f of n minus 1 plus f of n minus 2. So this is going to be the recurrence relation for this particular problem. Now we can clearly see that this can be modeled as a 1D array. Each cell stores the answer for reaching bottom from that cell, and the answer in cell X is just the sum of answers in X minus 1 and X minus 2. So let's say that our array is of size 4, 0, 1, 2, 3. So 1 will be storing total number of ways for reaching from 1 to 0. 2 will be storing number of ways for reaching from 2 to 0. And this answer will actually depend on the answer stored in 0 and 1. Again, 3 will be storing the total number of ways for reaching from 3 to 0. And the answer stored in 3 will depend on the answer stored in 1 and 2. So simply using the previous calculated answer, we can calculate the answer for the current step. And again, with the base case being that cell 0 and 1 already have 1 hard coded in them, because when we are at 0 and when we are at step 1, there's only one way of reaching the bottommost cell. So let's go through the code for this solution as well. So as we discussed, we have declared a vector of size n plus 1. So if we want to calculate the number of ways for going from n to 0, the answer for that, or the total number of ways, will actually be stored in the cell with index n. So that's why we have created an array of size n plus 1. Now we simply apply our logic. So in the cell 0 and 1, we have hard coded the value 1, because there's only one way of reaching the bottommost cell from 0 and 1. Now for all the other cells, we calculate the answer step by step. So the answer at the ith index will be nothing but the sum of answers stored at I minus 1 and I minus 2, because n depends on n minus 1 and n minus 2. And that's how simply we build our answer step by step. And finally, the total number of ways for reaching from the nth step to the 0th step will be stored in the last cell. So we return the value stored in the last cell as the final answer. Now let's try to analyze the time complexity for our DP solutions. So in the tabulation approach, it is pretty easy. We are filling up a 1D array of size n plus 1. So the total time and space complexity both are big O of n. In memoization, we are calculating the answer for each subproblem 1. So the different subproblems that we are solving are n, n minus 1, n minus 2, till 0. So there are total n plus 1 subproblems, and we are calculating the answer for each problem once. And also the calculation of answer for each subproblem takes O time, because we need to simply add two values, and addition is a O of constant operation. So the total time complexity for the memoization solution is also big O of n. So I hope you understood the logic behind using DP for this problem, and also the implementation details. Also, we are going to solve a lot of problems on DP in this series, so stay tuned. And I hope to see you in the next video. Thanks for watching, stay safe and keep learning. Bye bye.